Before we talk about the inverse trigonometric functions, we need to talk about inverse functions in general. And in order to talk about inverse functions, we need to talk about functions. What is a function? A function is this mathematical process by which you get an input value. There's some sort of rule or calculation or something that you do that ultimately leads to an output value. So for example, the squaring function takes a value and squares it. An inverse function is an attempt to undo this, to try to go backwards from this calculation. Now, in some cases, this is easy and it makes sense. In other cases, there are some complexities. And the x squared function is an example of some of those complexities. Here's what we mean by that. If we take the number 3 and square it, that would give us 9. Well, let me actually write it like this to be consistent. 3, we do our rule and we square it. Negative 3, if we do the rule, will also end up with 9. If we try to turn this around, the question is, what should 9 point back to, 3 or negative 3? It can't be both, because if it's both, then it's no longer a function. And so we have a situation here where we have multiple values mapping to the same output. And then if you try to undo that, we run into problems. So the question is, what do we do about that? Well, in some cases, we just say, well, the inverse doesn't exist. But in other cases, it is useful to have an inverse, or at least an inverse for at least part of the values. And that's what we get into with the x squared function. You might remember the graph of the parabola, y equals x squared. And you might remember that there's a relationship between the graph of a function and its inverse. The inverse function is the mirror image of this across the line y equals x. And so that would look like this. Now the problem with this, as you can see right away, is that this fails the vertical line test. This thing right here is not a function. So what do we do about it? Well, mathematicians say, well, sometimes we just have to make a decision. Which part of this do we care about more? And so we often throw away this bottom piece right here. And you might recognize the square root of x function. I'll just graph it here on its own. Is just that part of it. That part is actually just half a parabola on its side. And what we've done is we've said, okay, we're going to pick a value of this inverse function. It's in some way that's useful. And what's useful for us is to have the positive value be the thing that we talk about. So when we say square root of 9, we mean 3 and not negative 3. And that's also why we explicitly have to write plus or minus in our equations when we solve equations. Because when we write that square root function, it really only does refer to this upper half. It doesn't refer to that lower half. And so we explicitly have to say, but there's another possibility. And we're going to take these ideas and push them forward into trigonometry. We're going to start with the inverse sine function. Now, before we can do this, let's go back and remember. The sine function, we have some sort of input angle. We do some sort of process, and we get some value here. Now, there are a lot of different ways we can set this up, but the one that we're going to focus on is to think about the unit circle. With the unit circle picture, what we do is we draw our unit circle. We draw the angle theta, and that line will intersect the circle at some point. That point is x comma y. And then the sine function pulls out the y coordinate. Our interest right now is to do the inverse sine function, which means to go backwards. Given a value, can we generate an angle? So we'll draw it down here. So here we have a unit circle, and we are giving it a particular y value. So this is just some y value right here. We're going to ask the question, what angle will generate that y value in this process? And you can immediately see we're running into a problem just like we ran into with the square root function, which is that there are actually multiple angles. There's an angle over here and an angle over here. Both of these will give us that particular y as the output. So which one are we going to choose? Well, somewhat intuitively, it kind of makes sense that we'd pick the one that's over here in the first quadrant. Somehow jumping to the second quadrant doesn't really make sense, and we'll see another reason why this is sort of the better choice. But you can see that we can find some angle that generates that value. And there are a few things to observe. First of all, if y is too big, it doesn't intersect the circle at all, so no value of angle, no value of the angle will work. If you pick a value that's too small, same thing. So this is already teaching us about the domain and the range of this function. The inverse sine function this has a domain of -1 to 1. Because as we draw these horizontal lines, the lowest line that will actually pick up an intersection point happens at -1, which is the bottom of the unit circle, and then the top is at y equals +1. So the domain is plus or minus 1. Now the range, this is the output value. How do we get this? Well, the idea here is that we would want inverse sine of 0 to be 0, because then we're pointing to the right, not to left. Like, this is the natural thing to do. And then we're just going to trace a continuous piece from here up to there, and here down to there. The range of angles we get doing this and doing that is going to be from -π/2 to π/2. We also want to see how this inverse sine function works from a graphical perspective. Specifically, we want to look at the graph of the function. So here's a graph of y equals sine of theta. So input value theta. Sine function starts at 0, starts off going up, comes down, goes up, and then same thing in the other direction. What is the inverse function going to be? Well, remember, the inverse function is a reflection across the y equals x line. I'm going to extend this axis. So we're going to draw the y equals x line. And what we need to do is we need to think about how this thing looks when it reflects across that line. Now, this visualization is not necessarily easy for a lot of students. It just sort of depends on what your background is. Some students, actually, it helps if they make that y equals x line vertical by actually tilting their head, because it's easier to see the reflection. Another thing you could do is actually do some point-by-point stuff. So, for example, this point right here is on the line, so it stays. If you reflect it, let's take this point right here. This point moves up here. And this point over here moves down here. And in between, the general shape of the graph is just sort of waving back and forth. And in this case, you can see that this part is going to reflect over here. So we're going to get something that looks something like this. And that would be the inverse function. Well, I say would be because if we look, the vertical line test will fail for this. And so just like with the square root function, we need to pull off different parts of it. I'm going to, let's see, I'm going to cut it off here and here. Basically, we're cutting it off before it sort of loops back on itself and before it loops back on itself. Now, we could do a lot of work by doing more point-by-point stuff, but basically, you should be able to see that that peak here corresponds to π/2, which means that this would correspond to π/2 up here. And then down here, we'd have -π/2 corresponding to this, and that gets reflected over here to -π/2. And we can see that this has the exact same features as we talked about earlier when we were drawing the picture. The range goes from -π/2 to π/2. The domain, the input values, goes from -1 to 1, because this point right here, the height of it is 1. And so when you reflect it, that corresponds to 1 over here. And then same thing over here with the -1. And so if we look at the graph of the inverse sine function on its own, what are we going to see? We're just going to see this part right here. So I'll draw it over here on its own. Right, so this is at height π/2, height -π/2, that's 1, and that's -1. And this is the graph of the inverse sine function. You can do a similar process with the inverse cosine function. We're not going to show all the steps here, just the final result. So the cosine function, remember, it starts at 1, goes down and goes up again, and so that 1 point is over here. The domain and range being, the domain being -1 to 1 is the same as the sine function. The range from 0 to π is different from the inverse sine function. So it's worth taking a look at the picture for that. So let's say that we have a unit circle, like this. The domain being -1 to 1, that corresponds to picking x values between -1 and 1. And if we pick values that are further to the right or further to the left, we're not even going to get points on the circle anymore. So that part makes sense, the domain being from -1 to 1. Why is the range from 0 to π? Well, let's think about this point right here. The inverse cosine of 0, well, the x value for that is 1, as you can see right here. Now, which quadrant would we want to track through? Would we want to track through the first quadrant or the fourth quadrant? Typically speaking, we tend to think of things in the first quadrant. We did that with the sine and cosine function values in the first quadrant. We did this using reference angles to refer angles back to the first quadrant. So it makes sense to want to use values in the first quadrant. And as we keep drawing more of these vertical lines, you can see that we trace out this upper half of the circle, which goes from angle 0 to angle pi. And that's why this is our range. And so the same ideas come to play for the cosine function. It just, instead of looking at the lines y equals something, we're looking at lines x equals something. Here's the graph of the inverse tangent function. Now this has a couple features that didn't show up in the inverse sine and inverse cosine functions. One of the things about the tangent function is that it has the vertical asymptotes. When we reflect those across the y equals x line, those become horizontal asymptotes. And if you think about the locations of those asymptotes happen where the denominator is equal to 0, so where cosine is equal to 0, and that happens at negative pi over 2 and pi over 2. And so there's actually a whole stack of these curves just copied over and over and over again, corresponding to the periodicity of the tangent function. We're interested in this one because it goes through the origin. Again, sort of picking the quote-unquote right points to look at. And so the domain, because we can go as far to the right and as far to the left because of these horizontal asymptotes, the domain is the whole real line. Any number has an inverse tangent function. The range is negative pi over 2 to pi over 2, but not actually equal to those values, so that's why we have round parentheses here. And that's what happens with horizontal asymptotes. And so this is the graph of the inverse tangent function.